So today is, if I'm not mistaken, lecture 17. And we were discussing Lie groups and geometry. So apologies to those who have already seen the introduction to the subject in the previous class, but it's worth listening to twice. Okay, so Lie groups have very important applications in differential geometry. Have, I should say, many important applications. In differential geometry. Okay. In fact, a lot of the breakthroughs in Lie groups came because of its application. Okay. Now, the group themselves are manifolds, right? So they themselves, they are also rich in geometric structures. Okay. So it'll take this is a vast topic, and it'll take a whole course in itself, an advanced course nonetheless, to even touch upon these ideas. So for this course, we are just going to be limited to a few ideas, and one of the ideas is that the symmetry group of manifolds. Okay. So let's just do some intuitive exercises. So let's take a two-sphere. So let's embed this two-sphere in three-dimensional space. So the origin of the three-dimensional space coincides with the origin of the two-sphere. So this is S2. This is I, this is J, and this is K. Right. So now, the thing is that if you now apply, so this is a vector that whose end sits on the two-sphere, right? So this is basically a position vector which denotes a point on the two-sphere. So now if I represent that vector by saying, sorry? Okay, there's a lot of background noise. Somebody is talking. Can you just mute your microphone, please? Okay. Okay, all right. I thought that was a question, but it was actually, yeah, so, okay, anyway. So, no worries. So, yeah, no worries, yeah. So this is basically a vector R, let's call it R. So now if I take G and apply it on R, then I get another vector R prime. And as long as G is in the group SO3, we are guaranteed that the vector R prime is also on the two-sphere, right? That's how we defined SO3, right? So this is basically just a rotation, some sort of a rotation matrix, right? So this rotation is parameterized by some group element G. So if R is an arbitrary point on the two-sphere, we see that R prime is also an arbitrary point on the two-sphere. So not only that, the two-sphere looks exactly the same regardless of how you rotate it, right? If you rotate the whole two-sphere, it looks the same. So it should be kind of an intuitively obvious fact that SO3 is the symmetry group of two-sphere, right? I haven't really told you what a symmetry group is, but what I'm trying to, but you should be able to understand the statement somewhat intuitively. That if I take a two-dimensional sphere and rotate it by applying on it some element of SO3, we get another space which looks exactly like the space before. Because every point on the two-sphere looks like every other point on the two-sphere, right? So this is basically just to motivate that groups are somehow involved in capturing the symmetries of spaces. So let's look at another example where, instead of, say, a two-sphere, we have, say, an oblong-shaped object, okay? So it's like a squished two-sphere. Right. Now we see that the symmetry of this object has been reduced, right? Can somebody tell me some of the continuous symmetries of this object?
Rotation on z-axis.
Right. So it is still rotationally invariant around the z-axis, right? Is that clear to everyone? That we can still do this rotation. So Farhan, what is the name of the group under which it is still invariant?
SO1.
There is no such thing as SO1, but you're close.
SO2.
SO2, very good. Okay, good, very good, both of you. So SO2, so we see that for this kind of, egg-shaped object, so to speak, the symmetry group has been reduced down to SO2. And because I've drawn it in a particular way, there might be more symmetry, such as there could be a discrete symmetry in which, this point rotates to that point and that point rotates to that point, right? And so there could be some discrete, say, Z2, but I'm not interested in that right now. So for an egg, symmetric egg, we see that the symmetry group has been reduced to SO2. And then if I then say, this object, some blob, that's not going to have any symmetries, right? Some arbitrary three-dimensional blob, right? It won't have any obvious symmetry. So that would be a space which does not, a two-dimensional, closed surface. It's not going to have any symmetry. So we see that one way of characterizing spaces is by their symmetry groups. Okay. So we want to formalize some of these concepts. So here what we're seeing is that we are seeing that this is the action of a group on some space, on some manifold, right? So let us start by defining the group action on a manifold.
Does one manifold has only one symmetry group?
Does one manifold have only one symmetry group? Yes and no. Yeah. So there are different ways of defining a manifold. I mean, for us, we are defining a manifold to be a space as well as a metric on it. A metric meaning that it has some notion of distance on it. Given that we have this two, then yes, a manifold will have only one symmetry group. But you know, the same space can have different kinds of metrics. Then the symmetry group would be different. So if you just think of the manifold without the metric, which of course, then you know, it may admit a metric, but it can have more than one metric, then that would have different symmetry groups. Okay.
Okay, got it.
Okay, so, but yeah, for us, you know, essentially we want to think of symmetry groups as being unique to a manifold, yeah. Okay, so let's define the group action on a manifold. So let G be a Lie group and M a manifold. Okay, so a manifold is a topological space which is locally can be covered by charts which are subsets of Rn. So the action of the group G on M is, it's a map from the group and the manifold to the manifold such that this action should have this following properties. Number one, if we take the identity element of the group and apply it to some point on the manifold, then we get the same point back. And that should hold true for all points in M. Okay. And number two is, so if I have two actions of the manifold composed with each other, so we have some sigma, some action of some group element G1 on some point P. Of course, this itself is some other point or the same point or whatever on the manifold. So if I apply to it another group action using G2, then this, so this is a composition of two group actions. That should be the same as G1, G2. This is the group, this is the group multiplication acting on P. Okay, so this is basically, these are the two properties that the group action has to satisfy. Okay. Okay, let's you know, talk about some examples. So, you know, let's take a position vector X in Rn. So X is basically just a column matrix with n real entries, right? And let G be an element in the Lie group GLN, comma R. Okay. So then, you know, the action of G, we then, you know, let us define an action of GLNR on Rn to be just the matrix multiplication of G acting on X, right? So it should be clear that this is also an element of Rn, right? Because this is an n by n matrix. And and this is an n-dimensional column matrix, right? So the matrix multiplication is going to give me another column matrix, right? So the output is also an element of Rn. And because we have taken G to be an element of GL and R, it's of course, it's a group action. Okay, so we can just extend this map, this action. Or limit to this action in such a way that, this action to the action of SON, which is a subgroup of, say, GL and R, right? On Sn-1, which is a subset of Rn, right? So, and then I gave you an exercise, and you should work this out. And the exercise is that, so if you have an X in Rn such that the modulus of X is 1, then you should show that G acting on X, for all G in SON, constitute a group action. So I've given you the definition of the group action. What do you have to do to show this exercise? You just have to verify that those two properties that are part of the group action definition are satisfied, right?